Welcome, learners. My name once again is Mr. Pochilola. Welcome to this revision series in which we are going to be looking at the past exam papers, including mock papers as well as manable papers. All right, so welcome to this session in which we are going to be revising chemistry paper, mock paper, which is written in 2023 by schools from the Central Eastern Education Division. Right, these schools include Imponera Secondary School, Maloa, Chipoka, Kotakota, Ngamenya Girls, Kafukule Secondary School, Vera, just to name but a few. All right, so the structure of the paper. Start looking at the cover page here. All right, there's space for your exam number. So if you are a candidate, let's say that your school number is M2040 and your candidate number 002. So you indicate your number there. All right. And take note that the subject is chemistry. The subject code for chemistry, Msce chemistry, is M036-1. This is paper 1. Remember, M stands for Msce. All right, and this paper is to be done in 2 hours' time. Two hours is from 8 o'clock to 10 o'clock. That's fine. Also take note of the date in which it was written. This was Tuesday, 28th March, 2023. Paper 1 has 100 marks, which come from 2 sections, namely Section A and Section B. Usually Section A has 70 marks and Section B has 30 marks, which gives us a total of 100 marks. All right. So check the paper has 2 sections, sections A and B, and contains 13 questions. I'm sure we have 10 in section A and 3 questions in section B. So take note of that. That's the structure of the paper. Without wasting your time, let's go to the questions, starting off with section A. So question 1, section A, is asking us to define a pure substance. This must be from Form 3 chemistry. Define a pure substance. So a pure substance is defined as a substance with constant composition. The simplest definition of a pure substance is a substance with a constant composition. All right, so take note, this is 1 mark. If you say this correctly, you have 1 mark there. Or you'd say is a substance which is not contaminated or which does not contain any other substance except the substance itself. That's also a definition of a pure substance. All right, that's great. Question B. All right, question B. Table 1 shows substances A, B, C, and D, and K with their relative flow values. All right. Okay, so substance A has 3 values. Therefore, this is not pure. A pure substance has only one relative flow value. Okay, so this is not pure. This one is pure. Why are we saying it's pure? Because it has only one relative flow value. All right. C has 2, therefore it's not pure. Not pure. And just to use the symbols not pure to mean NP, not pure. This is pure. This is not pure. Pure, and this is not pure. Just to refresh your mind, relative flow value RF is defined as distance traveled by sample divided by distance of the solvent. That's the definition. So in a chromatography experiment to determine the purity of a substance, you look for relative flow values of the samples making up the substance under analysis. All right, so if a substance has 3 values, relative flow values, it means such a substance is not pure. A pure substance has only one relative flow value. Therefore, A is not pure. It's not pure. Why? Because it has 3 values. B is pure because it only has 1. And the C is not pure because it has 2. D is pure because it only has 1 relative flow value. And the K is also not pure. A pure substance has only one relative flow value. So in this case, to answer the question, pure substances include B. So we have B and D. B and D are pure substances. Why are we saying so? Because B and D have only one relative flow values. All right, so a pure substance always has only one relative flow value. If it has more than one, it means that such a substance is not pure. So that means the rest are not pure. They are impure substances. So in this case, we have A, C, and K. A, C, and K are not pure substances. Why? Because they have more than one relative flow values. That's very important to note. All right, can proceed. Work out the distance moved by a solvent front. In D, if the distance moved by the substance is 40 millimeters. All right. So remember that relative flow value written as RF is distance moved by sample divided by distance moved by solvent. Okay, so for the substance D, all we have to do is substitute the given values. We are told it's 0.85, so we get 0.85. Distance moved by sample or substance is 40 millimeters. 40 millimeters, and we are asked to find distance moved by sample, solvent. Distance of the solvent. So distance of the solvent. So all we have to do is make distance of solvent the subject. All right. So in this case, make it the subject. It means the distance is going to be 40 divided by 0.85. Yeah, this in millimeters. So whatever you find, that will be the distance moved by the solvent. Okay, the solvent front. Okay, so make sure you know this. The basis is the formula definition of relative flow value, which is distance moved by sample divided by distance moved by the solvent, which is called the solvent front. So we are already told that relative flow value for sample D or substance D is 0.85. All right. So all we have to do is substitute and calculate the distance of the solvent. You should be able to find 40 divided by 0.85 is 47. So the answer is 47. So using a calculator, you should be able to find 47 millimeters. All right, so let's see how to go about this kind of problem. 3 marks. Where are those 3 marks coming from? By writing the formula right down, that's 1 mark. Correct substitution, 1 mark, and the 1 mark for the correct answer. So 3 marks there. All right, I hope so far so good. Question number 1E. We can erase this bit. 1E, we are asked to, question 1E, describe how we can test hydrogen gas. Test for hydrogen gas. This is coming from the same topic, experimental techniques, form 3, chemistry. All right, so in order to tell that a given gas is hydrogen gas, all we have to do is, okay, so we have a container, let's say a test tube, suspected to contain a certain gas. Okay, in this case we are told it's hydrogen gas. All right, so what we do is you simply get a burning splint, like a burning matchstick. This is a splint, a burning splint, burning splint, a burning splint, like a matchstick. You light a matchstick and get it closer to the mouth of the test tube. If the gas in the test tube is hydrogen, then you are going to hear a pop sound or a small explosion. Because hydrogen is explosive, so you must get a small explosion. We call it a pop sound. It goes like pop, pop. So when you have a small explosion like that, upon bringing a burning splint over the mouth of a test tube suspected to contain hydrogen, then it means that the gas in it is hydrogen if it makes a pop sound. All right, so we're saying bring a burning, you can say place, not bring but place. So place a burning splint, A burning splint is like a burning matchstick over the mouth of the test tube containing the gas, containing the gas. All right. If it makes a pop sound, then the gas is indeed hydrogen. All right, so place a burning splint, or you can say burning matchstick, over the mouth of the test tube containing the gas. If it makes a pop sound is like a small explosion. It goes like poof, poof. All right, then the gas is hydrogen. Okay, so you can find a way of shortening this because the space is just small. So you don't have to write an overflowing text. Okay, so just say a place a burning splint on the mouth of test tube. A pop sound is produced if the gas is hydrogen gas. All right, so that's how to answer this question. 2 marks. Make sure you mention these both parts. Each part is 1 mark, which gives us 2 marks there. Please pay attention to the number of marks. I always like to say that because the number of marks always indicate how many points you need to write down. All right, number 2A, we are asked to distinguish between oxidation reaction from reduction reaction. Oh, this is like a redox reaction in terms of electron transfer. All right, so oxidation, remember, is the gain. So oxidation is the loss of electrons. Okay, that's 1 mark. Oxidation is loss of electrons, while reduction is gain of electrons. All right, you say oil rig, oil rig. So using oil rig, oxidation is loss, reduction is gain. In terms of electron transfer, yeah. So oxidation is loss of electrons. When a substance it loses electrons, it means that substance is undergoing an oxidation process. So recall the use of oil rig. Yeah, so oxidation, start with oxidation. So oxidation is loss of electrons. All right. Reduction is gain of electrons. So don't forget this definition, and also remember that you can define these terms using, in terms of gain or loss of oxygen. Oxidation is gain of oxygen, and reduction is loss of oxygen. Okay, so now all the definitions so that you are able to give any one of them depending on the circumstances in which you are asked to give. All right, B, the following is the chemical equation for the reaction between magnesium. So we are told magnesium is reacting with who? With what? Silver nitrate. Okay. All right. Okay, so the question is, okay, maybe before it was the question, we have magnesium in solid form and silver nitrate in solution form or aqueous. So the product will be magnesium nitrate and silver metal. Okay, that's good. All right, so write oxidation half equation. In other words, we need to show the oxidation process. Okay, so to begin with, you need to write this equation in ionic form. So magnesium is solid, so it's written as MgO with a superscript of 0, okay, reacting with silver. So in solution, we have, in solution form, it means we have silver ions and the nitrate, two silver ions and the nitrate ions. Take note. The products will be magnesium. So notice that magnesium is going to be magnesium Mg 2 plus. Why? Because this subscript here is telling us that in order to form magnesium nitrate, we must have magnesium ions Mg plus, Mg2 plus, and the nitrate ions, and then 2 silver, which is solid. All right, so from this equation we can identify the ions that have been reduced, or the ions that have been, the species that have been oxidized. All right, so in this case, if you look at what has happened to magnesium, initially magnesium was neutral. Mg0 means before losing electrons, but then after the reaction, you find that it has turned to magnesium ions, Mg2 plus. That means it lost 2 electrons. Therefore, we will say that magnesium has been oxidized from Mg0 to Mg2 plus. So that's oxidation. Therefore, the equation, the half equation, is going to be Mg solid turning to Mg2 plus 2 electrons. Yeah, so that's the oxidation half equation. In this case, it is magnesium ions, magnesium metal, which has been oxidized. How do you know that? Because its oxidation number has changed from 0 to 2 plus. So we have Mg0 turning to Mg2 plus 2 electrons. Don't forget to add the 2 electrons, because otherwise you end up having an equation which is not properly balanced in terms of charges. Identify a reducing agent. All right, so we needed to identify which one has been reduced. In this case, if you look at silver, silver has a positive 1 there, but the metal part, the product, is 0 there. That means silver has been reduced. Magnesium has been oxidized, yes, as we saw in the equation here, but silver has been reduced. How do we know that reduction has taken place? When the oxidation state decreases from positive to 0, it means there's a reduction there. So what has caused this reduction is the magnesium. So magnesium has caused silver to be reduced from positive 1 to 0. So in this case, it is going to be magnesium. All right, magnesium is the one which has been reduced. The one that has been reduced. Okay. Let's continue. Work out the oxidation number of chromium in a dichromate ion. So we are told the dichromate ion is Cr2 or 7 2 minus. All right, so we needed to apply one of the rules of writing oxidation numbers, which says that for a complex ion, the sum of the oxidation numbers is equal to the charge on the ion. Okay, so in this case, let's say that the oxidation state for chromium is X. So we shall have 2X plus, let's say that of on oxygen. We are already taught that of oxygen is on oxygen is 2 minus, but they are, all right, there are 7 oxygen atoms. Therefore, we shall have 7 multiplied by minus 2, and this must be equal to minus 2. All right. Ask me where I've taken the minus 2 from. That's the charge on an oxygen atom, which is embedded to a metal ion. So in this case, we shall have 2x. We need to solve for 2x. We need to solve for x. 2x minus 14 is equal to minus 2. All right, so in this case, take 2x. This must be equal to minus 2 plus 14. Minus 2 plus 14, which must be 12. So 2x, therefore, is going to be equal to 12. Divide both sides by 2. So x, therefore, is going to be equal to 6. But it has to be plus 6. So in this case, the oxidation number on the chromium is positive 6. Positive 6. Okay, you may not need to show all these steps. If you want, you can shorten them. All right. I'm saying this because there are only 2 marks indicated here. So you are going to apply the rule, one of the rules of oxidation numbers right away. So 2Cr, just say that, minus, okay, plus 7 multiplied by minus 2 is equal to minus 2. That's 1 mark. All right, so we have 2Cr minus 14 is equal to minus 2. That could be another mark. So solving for Cr, that means the oxidation state on a Cr chromium is going to be equal to, if you solve this equation, you take minus 14 to that side, it will give you 12. So dividing by 2 thereafter, it will give you positive 6. All right, in case you have questions, don't forget to comment in the section there, in the comment section. I'll be glad to address your issue quickly if need be. All right, number 3A, 1, define an acid according to the Rowley-Bronsted theory. Remember that there are many theories used to define acids or bases. One theory, which you met in Form 2, is known as the Arrhenius theory. According to the Arrhenius theory, an acid is any substance which releases hydrogen ions in solution, and a base is a substance which releases hydroxide ions in solution. But in MSCE and beyond, we shall define an acid using a theory known as Rowley-Bronsted theory. The Rowley-Bronsted theory states that an acid is a proton donor. All right. So straight away, without wasting much time, an acid is a proton donor. Proton donor. Okay, so they may also ask you to define a base in the same way using the Rowley-Bronsted theory. A base is a proton acceptor. So the proton in most cases is just a hydrogen ion. Okay, so an acid donates hydrogen ion. So a hydrogen ion is called a proton. It's called a proton. All right, so any substance that donates a proton in a chemical reaction is called an acid, according to the Rowley-Bronsted theory. Part 2, identify acid-base conjugate pairs in the equation below. Remember that a conjugate base is a substance which is formed when an acid has donated a proton. What remains is called the conjugate base. Okay, and the conjugate acid is the product, or what remains when a base has gained a proton or accepted a proton. I just revised those definitions. So in this case, let's identify the species. So in this case, hydrochloric acid is an acid. Upon donating its hydrogen proton, Cl minus, which is chloride ion, remains. Therefore, the pair is going to be HCl stroke Cl minus. That's the first one. Notice that the Cl minus is formed when HCl has donated its hydrogen to water. So the water molecule receives the hydrogen that the water molecule receives hydrogen from HCl, and a hydronium ion is formed, which is H3O plus. Therefore, in this case, the H3O plus is acting like an acid. So when you're writing down the pair, you're going to have H3O positive stroke H2O. All right, remember that you start by writing the acid part first, followed by the base part. If you need more lessons on the conjugate acid-base pairs, don't hesitate to ask me to teach you this again. I'll be glad. Just tell me on my number 098-125-8577. I'll be glad to attend to you. All right. Part B. Complete the equation by filling in conjugate acid-base pair. So first and foremost, you need to identify the acid. So the assumption being made here is that the acid is this acetic acid, which is vinegar. So it will donate hydrogen, and that hydrogen will be received by H2O. So in this case, we shall have, what will remain is CH3, COOH, sorry. Yeah, this hydrogen will be removed, it will go there. Okay, so what will remain is minus. Yeah, when a hydrogen has been knocked out of an acid, the minus ion is formed. Okay, so the other product will be the hydronium ion, which is H3O positive. All right, why positive? Because the hydrogen that has been donated by the acetic acid will add to the hydrogen ion atoms which are already present in water. It will make 3H3. And since a proton is positive, therefore the sign here is going to be, the charge there is going to be positive as well. All right, any questions? If you know questions, thank you very much. Let's continue to question number 4. Define the term rate of reaction. Define the term rate of reaction. So rate of reaction is just the speed of a chemical reaction. That's all. Rate of reaction is the speed of a chemical reaction. Yeah. Okay. If you want, you can leave your answer like this. Rate of reaction is the speed of a chemical reaction. But you can also say this. I want you to understand the different ways of defining the rate of reaction. You can also define a rate of reaction as amount of product formed per unit time. That's also a complete definition of rate of reaction. Or alternatively, you can say it is the amount of reactant consumed, because in a chemical reaction, the reactants are consumed while products are formed. So in terms of reactant, you can say it is the amount of reactant consumed per unit time, or simply it is the speed of a chemical reaction. You still get all the full marks there. All right. I hope you're happy. I'm happy as well. Okay. So table below shows the volume of a gas produced during a certain reaction within a specified time. Use it to answer the questions that follow. Okay, fine. Plot a graph of volume of gas produced against time in seconds. Okay. Wow. So we have values of volume, and the values of time there. So that means the volume of gas is going to go to the y-axis and time x-axis. Watch out. The variable that is mentioned before the word against should be plotted on the y-axis, and the one that comes at the end should be along the x-axis. In other words, the dependent variable should always be plotted on y-axis, and the independent variable, which is time, should be in the x-axis, plotted there. All right, so this is just a matter of plotting graph. Take note of the scale, the values which are going to help us decide on the scale, choice of scale. All right, so first of all, let's label. So volume, the third volume should be on the y-axis, and the volume is in units cubic centimeters. So cubic centimeters, label your graph properly. And then you have time in seconds. All right, so we just labeled our graph, the axis of our graph. Now let's put a scale. Time ranges from 0 to 15, to 45. So we can have intervals of 5. So we have 0, 5, 10, 15, 20, 25, 30, 35, 40, up to 45. Yeah. And then time, the same way. Not time, but what? Volume. Volume is from 0 to 30. We have to be careful there. We can have a scale of 5 to 30, no problem. Yeah, so we can also have 5, 10, 15, 20, 25 to 30. Okay, yeah, to 30, that's okay. So scale, we're done. Now let's plot the graph. Okay, for 0, at time 0, the volume is 0. Okay, so we can have our first point here. Okay, and after 5 seconds, the volume is 15. So that must be somewhere here. All right, when the time is 20 seconds, volume is 27. We need to be careful there. So we have, when the time is 20, 27, 20 is, 20 is somewhere here, so we need to determine 27, 25. Okay, first of all, what is the value of each division? We need to determine that. From 0 to 5, there are 10 divisions. That means each is 0.5. Okay. Yeah. Each small division is 0.5. So 27, this is 25. Okay. So in order to get 27, we shall need 4 of these. 4 divisions from 25. We need to find the point. Our point is going to be somewhere there. Yeah. Okay, next, we need another point. When it's 24, the time is 25. The time is 25. The volume is 28. So 25, we need 6 of these. 6 of these, 25, 28. From 25, we have 1, 2, 3, somewhere there. 6 of these. Somewhere there. All right. When the volume is 30, the time is 30 minutes, 30 seconds. The volume is 30 also. So it's somewhere here. All right. And when the volume is, the time is 45. The time is 45 seconds. The volume is 30. Okay, somewhere there. Okay, then next we draw in a curve of best fit, joining the points. So all you need to do is join the points neatly. Okay. Yeah, so you need to join the points. using a line, okay. So just have to draw a curve. There we go. So that's what we have. Oh, yeah, we can have that because here it is straight a little bit, but it's supposed to pass through the point here. Yeah, so that's what we have. Okay, that's our graph. Calculate the rate of reaction after 5 seconds. After 5 seconds, all now we have to do is, when they say after 30 seconds, it means we are looking at this part of the graph, this one. Yeah, from here to somewhere there. So all you need to do is draw what is called a tangent. You simply draw a tangent, just to draw a tangent which joins this part. Sorry. Draw a tangent. Remember our curve is like this. So all we have to do is, of course, with some degree of error, but it should be sufficient to find. Okay, so just to draw a line, straight line joining those 2 points, and then in order to find the rate, you take the gradient. Find the gradient. Find the gradient of this line. Just find the gradient of this part. So take the change in volume divided by the change in time. So whatever you get is going to give you rate. So find how much this is. Take the value there minus the value here, which corresponds to somewhere there. This should be 28 or something, minus maybe 12. Okay, so 28 minus 12. Then you divide by the time taken, which is, in this case, you take the time here is 20. This is 20, and this time here is roughly 5. So you have 20 minus 5. This is just rough calculation, since I'm not quite exact in the determination of the points there, but that's how you can do it. So you have 26 divided by 15. 26 divided by 15. 26 divided by 15 is roughly 1.7. So the rate, therefore, is going to be 1.7 cubic centimeters per second. Don't forget the units. It's cubic centimeters per second. All right, so you can do that. You can ensure you're working there without problems. Okay, I would like to leave you now, but before that, let's do this last part, and then when we meet again, we shall look at the rest of the questions. We're still doing section A. Draw a structure of pentanol. Pentanol, this is an alcohol, which has 5 carbon atoms. The rule for drawing structures, this is a tertiary alcohol. Okay, so if it's a tertiary alcohol, what it means is the OH must be located at a carbon atom which is also surrounded by other carbon atoms. So first of all, remember, alcohols can be tertiary, primary, secondary, and tertiary. Yeah. So in this case, it means our alcohol must have two branches. Yeah, must have two branches. So we need to do that. We need to have a carbon atom, another carbon atom at the end, and another carbon atom there. So the OH is positioned at a carbon atom which is attached to two other carbon atoms. The OH group is attached. Let me do this. Yeah, so we are saying that our tertiary alcohol, remember that the tertiary alcohol has the OH which is attached to a carbon atom which is also attached to three other carbon atoms, like that. All right, so in this case, our tertiary structure, tertiary alcohol, remember it's a pentanol, so it must have 1, 2, 3, 4, then 5, like that, so that the OH will be somewhere here, and then the rest of the hydrogen atoms will be attached to the carbon atoms, to the free carbon atoms. So in this case, we shall have an H here, another H, another H, like that. See, this also should have an H, H, an H, an H, another H, like that. So check that the number of carbon atoms and the number of hydrogen atoms is consistent with our formula here. Take note, so for carbon atoms, we have 1, 2, 3, 4, and 5. We are safe. On carbon atoms, we are okay. What about on hydrogen? We have 11 of them, without including the OH one. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes, there we are. So we are okay on this. All right, so let me redraw this one properly so that you can easily follow. Don't violate the numbers. So we have C, 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 C. You can put even a branch, you can put it here. Okay, you can put it there. So we have this one. The OH must come somewhere there. Then we have H, 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 H. Oh God. Yeah. H, another H. Check that the number of hydrogen atoms do not exceed that given in the formula. So carbon atoms, we have 1, 2, 3, 4, 5. Hydrogen, we have 1, 2, 3, yes, 4, 5, 6, 7, 8, 9, 10, 11. That's good. Don't forget that we are not including the hydrogen on the OH group. All right, so I would like us to stop here for now. When we meet again, we are going to continue with the rest of the questions. Remember, we are doing this just to give you confidence, to revise, to remind you. You can also go through the paper again and again. I'll share you the PDF, if you like, of this paper, so that you can also practice on your own, and let's see how far we can go together. Bye bye for now. This has been 1 hour lesson.